Hello, Math 120, and this is Professor Gonzalez, and I'd like to do some problems from section 8.2, which is taking a look at exponential functions. So I think the first thing we want to do is take a look at some of those exponential functions, or at least the definition of it. Definition of an exponential function is a function of the form f of x equals a to the x. Now, the thing that you really want to focus in on that makes this different, because we've seen functions before that were like f of x equals x to the second, right? Or x to the fourth, or different things like that. But now notice where the x is this time. The x is actually right there in the exponential, right? So there it is right there in the exponential. That makes it an exponential function. The variable is in the exponential position. And that does make exponential growth, which is very fast growth, or exponential decay, which is one thing that it means. Exponential growth is that it continues, it accelerates. The growth gets faster and faster every day, or whatever period of time you're talking about. Anyhow, and they've been talking quite a bit about that with COVID, exponential growth and things like that. But let's take a look now. Here's the definition of it. But I think we're going to go ahead and graph it for you so you can kind of get the idea of what's happening. But it says where a, here I am right here, where a, oops, I don't want that. It says where a cannot equal 1. Well, the reason why is because look at if a equals 1 and you raise to the first power and you raise to the second power and you raise to the third power, it's all 1. So the function would just remain constantly 1 the whole time, which that would not be an exponential function. So a cannot equal 1, but a must be greater than 0, okay? The domain of an exponential function is always going to be the set of all real numbers. Now they're asking us a couple times in this particular section for the domain. Whoops, man, I'm just struggling here. They're asking about the domain, and so they're going to say the domain for this exponential function is going to be the set of all reals, right? So that's going to be kind of almost a given thing, that when you have this exponential function, the domain is going to be all reals, okay? Let's go ahead and take a look at what a exponential function looks like. And a real nice basic one would be something like f of x equals 2 to the x power. So when we're actually going to, fill this thing out, trying to, that's our y value, also known as the, also known as the f of x, right? And you'll get kind of a sense of what's going on here. Let's put in 0. And 0 to the 0 power is just going to be 1. So then we put in a 1. 2 to the first is just 2. And you put in number 2, so 2 to the second is 4. You keep on going. So you put in a 3. And a 3 to the, the base is 2. The base is 2. So just so you can see where I'm putting this stuff, right? There's your x. There's our x values that we're putting in for the exponent. So here we are putting in a 3 in for x. And so it's 2 to the third, which is 2 times 2 times 2, which is 8. Okay, also, it's good for us to realize that what if we put in a negative value for x? Well, that would be 2 to the negative first, and we know that's just going to give us a half, right? So that gives us a bunch of values to graph that we can graph real quick. Let's see if I can try to make a half decent looking graph here. So there's our x, there's our f of x. Maybe that needs to be a little longer. That's our f of x. And so let's start off with our first point right there, 0, 1. And if you think about this, when you have a base, what if the base was 3? Well, 3 to the first power, 3 to the 0 power is 1. What if the base was 5? 5 to the 0 power is 1. So really, with these exponential functions, your y-intercept is always going to be 0, comma 1, unless there's some kind of vertical shift or horizontal shift involved. This is the basic parent graph right here. Okay, so we have 0, comma 2. We also have the next one, which is 1, comma 2. So 1, comma up, 1, 2. And then what do we have? 2, comma 4. There's 2, comma up, 1, 2, 3, 4. So we've got this kind of thing going on. We even had 3, comma 8. There's 4, 8's about there, I guess, doubling that. Yeah. Gee, a little off there. And then what happens to the left when we put this negative value in here? 2 to the negative first gives us a half. So this is 1, so half is right there. So negative 1 up a half is right there. So one thing that happens here also is that this gets closer and closer, but never crosses the x-axis. Okay, so remember we said that the domain is a set of all reals. Yeah, it goes forever to the left and it goes forever up to the right. So the domain would just be all reals. Now the range on this particular problem, it does not get to 0, right? We're talking about the y values. It does not get to 0, but it climbs up and up and up and up forever, so up to towards positive infinity. So there's our domain and range. That's a typical basic exponential function, okay? Now there can be our horizontal and vertical shifts like we had with parabolas. If I were to take a look at something like that, let's, before I do that, let me go down here and let's look at a property. And what I want to do is I want to highlight, do a quick highlight of this particular point, this particular point, and this particular point. So take a look at that, 0, comma 1, 1, comma 2, negative 1, comma 2. And actually, really should be kind of focusing in on the base there and that 2. And that actually will tell us what the base of the problem is. So let's go down here to a property. First of all, properties of exponential functions. This is for f of x equals a to the x, and this is where a is greater than 1, cannot equal 1. The domain is the set of all real numbers. The range is the set of all possible positive real numbers. And that's what this particular problem. Now, that's look at number, okay, there are no x-intercepts. The y-intercept is 0, 1. But this is what I was kind of trying to get at, is that if you put in negative 1, you're going to get 1 over the base, a. So notice a is our base. And if you put in 0, you'll get 1. Okay, that's our y-intercept. Let me write that down. And if you put in a 1, you get out a, the base. So when you're looking at a graph, in fact, we might just want to do this one down here right now that we got it right in front of us. Well, let's see. No, I didn't want to do that one. No, I don't want to do that one yet. I wanted to go up and start. So, so it's nice that we're able to come up with these points real quick, knowing the base, or vice versa, knowing those points going back to the function. But I'll go back to that again. Let's see. I think I'll refer back to this in a little bit. So let's go up here and start off. Now this is starting off with E. Now E right here, E sounds like it might be, you know, a variable, but it's not. E is reserved for a number, approximately 2.1, 2.71, blah, blah, blah. E is a number. It's an irrational number, a lot like pi, the other famous irrational number, right? If you look at its decimal representation, it doesn't have a pattern and it never terminates, so it's irrational. But E is one of those famous irrational numbers. It is a number, though. Don't think it's a variable. It is a number. They want to know what the number is. So what you can do is you could go ahead and stick it in your calculator, and that'll give us a good approximation. They're wanting us to round it to 5 decimal places. And how do you put it in your calculator? Well, you need to have a scientific calculator. They're pretty cheap these days. But when you put in the calculator, usually you gotta kind of search for it. But a lot of times they'll have this LN button, and above the LN button will be your E to the X button, something like that. Um, and that's because these guys are inverse functions of each other, and so the calculator likes to set up inverses. So so remember when you have usually it's like a different color, because then they'll have this shift button that's blue, and you punch the shift button and it activates the blue stuff. So then you have to hit this LN button, which activates this E to the X, and up pops on your screen E to the caret usually. And then what you do with that is then you have to, or someone will have like a blinking cursor, and then you put in a 1 and then hit enter, and your calculator will spit out approximately what it equals to, and it depends on how many decimal places your calculator can show. 718281828, and it goes forever. Remember, not having a pattern or terminating. They want 5 decimal places, so 1, 2, 3, 4, 5, and you look at the decimal to the right, and it's 1. So this is approximately 2.71 71828. Okay, just to give you a little bit more about where that comes from. This actually comes from a function that you'll see in the business world. You'll also see exponential functions in nature and growth and stuff like that, but business people like to really claim it. Anyways, it works well for continuous compounding continuous growth. Anyhow, 1 plus 1 over n, all raised to the nth power. That little expression right there, if you keep on putting larger numbers for n into that expression, so if you started out, and this takes a little while, but if you start at n equals, you put in a 1, what happens if you put in a 1? You get, if you put in a 1, you would get 1 plus 1 raised to the 1 power, you get a 2, right? And so you keep on putting bigger, you put a 10, then you put 100, then you put 10,000. You keep on putting larger numbers and larger numbers. And you're going to find out that you keep on putting larger numbers approaching infinity. And as those numbers get larger and larger, actually the number becomes E. It actually approaches E, let's just say. So that's the number. The number E seems kind of mysterious, but it just comes from making the n values extremely large, and when you make them very, very large, it ends up becoming E actually. So that's what that is. So E to the second power is our next one, number 2, part A. And once again, I just grab my calculator and then type in E to the second. And on this one, they want us to round to 3 decimal places, so we just get 7.389. And E to the negative 4th, once again, E, and depends, some calculators have a little blinking cursor. This depends on the maker of your calculator. And this one, you just want to put a negative 4 and then hit enter. And 3 places are going to be approximately 0.018. All right, so complete the following statement. The graph of every exponential function, f of x equals a to the x, passes through these 3 points. So they passes through infinitely many points, but these are 3 like really, really useful points, let's say. And that just comes from this definition right here, right? And here are the 3 points that they're talking about right there. Okay, and you could actually plug in values to get those 3 important points also. But remember what those 3 points are. I guess I'll put them right here. If you put in a negative 1, so let's focus in to this guy right here. If you had an A and you put in, so our x value is going to be what we're putting in, and you put in a negative 1. Well, remember, a to the negative first is just 1 over a. So that's why they're saying that will always happen. negative 1 comma 1 over your base a will always be there. Also, we also know that as long as there's no shifting involved, this is going to be 0 comma 1 is the y-intercept. And what's another, and in fact, you can see that happen too. Let's just make sure you're seeing that. If I said, okay, my function is a to the x power, what happens when I put in a 0 for x? Well, a to the anything to the 0 power, as long as it's not 0 to the 0, is 1. So we got a 1. And then let's also, look at what if we had a to the, so we had negative 1, 0, and how about positive 1? And a to the positive 1 is just a. And so the nice thing about this, which is really helpful, is that when you're looking at this, if you're looking at these points, or if you're looking at the function over here, whatever that base is, it's going to fit right into these places really quick. And I can graph 3 points really fast, negative 1 comma 1 over a, 0 comma 1, and 1 comma a. Okay, and so that's really nice. In fact, we're going to do that right here. They're asking us determine the exponential function whose graph is given. Well, kind of based on what I just learned on that last problem, if I take a look at negative 1 comma 1 over 2, and then I got my y-intercept right there, and then I've got 1 comma 2, I know that that's my a value, my base. So that must be the function f of x equals base 2 to the x power, right? Because there's our base of a, which is 2 in this case. So f of x equals 2 to the x. What about the next one? Maybe I'll zoom out a little bit. Using that same kind of idea, let's do that. Whoops. Let's use that same idea. Well, there's our y-intercept. This is really kind of a smashed graph. There's negative 1 comma 1 over 6. So there's that. And let's verify it, 1 comma 6. Well, that must be my a value. That must be my a value. And what's the a value? It is 6. So this is going to be f of x equals 6 to the x. And that's the function. And so we can really get some nice points quickly by having that information from right here, which is also listed in the properties of exponential functions. Okay, so now what? Okay, I already talked about that. I did my little spiel about that. There's what we just were talking about. Now I need to kind of talk about shifting, just because it's so much faster. You could always plot points, and that's something you could always do, but it's nice to try to tie some of this stuff from before. I'm going to go ahead and erase these pieces right here so I can show some more stuff. Okay, let's get rid of that. I'm going to keep the graph. And so this graph is f of x equals 2 to the x. And I think I'm going to get rid of some of that stuff. Okay, so that's really the parent graph, right? The basic parent graph. This thing should be growing, whoops, a little bit faster, I think. Whoa, man. Just don't touch it. It's the rule. That's better. Okay, so now what we're trying to do is we're trying to get you to see some things here. Like, for instance, what happens if we had a different function and we called it, no, it's got to be a different function, different name. How about we'll call it g of x. It's still going to be 2 to the x, so it's going to have that same exact look. But guess what happens if I give it a +1? What does that do? Well, it's the best thing to do is actually to go to this y-intercept, which that y-intercept was actually, that's a half right there. So let's just make sure that doesn't, so the y-intercept is right there at 0, 1. And what did it do to all the y values? It just moved it up. So we're going to call this, what is that? That's called a vertical shift. And we went up 1 for every point. So yeah, you could actually take this. There's 1, so then that goes to 2. And that was at 2, so that just goes up to 3. And that was at 4, so that goes up to 5. And that was at a half, so it goes up to 1.5. So you have this new exponential function that's just now. Here's another thing that's really important to see. Remember before, our original was going close but never crossing 0. Well, since everything shifted up by 1, my new green function is going to come down, 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 but never cross 1. So it has that kind of look. So we can do vertical shifts. If you have this plus 1 after, so we have 2 to the x, and then after that plus 1, go up 1. If it was plus 2, go up 2. If it was minus 5, drop it down by 5. Now, once again, you need to start at 0, 1 when you're shifting it around. Do not start at 0, 0, because that's not even a point on my graph. So that's a common mistake. And then another thing to see here is, let's call this h of x, another function, h of x, and let's call this, okay, it's still going to be like the same parent graph, 2 to the x. It's going to have the same look. But this particular one is going to be, we're going to put in here, let's put minus 2. And so what that is going to do for us is that's going to produce a horizontal shift. And it's going to be right, just like before. When you're affecting that x value, it's actually the opposite. Horizontal shift right 2. So if I was going to graph this, I would always start on the easiest point, is that y-intercept, and I'm going to move it over 1, 2. And so now this new graph, it didn't shift up, so it's still going to have this, it's basically like take that black graph and make this 0, 1, and now graph, right? And or you could also go up here at this 1, 2 and just move this over 1, 2 places. Would also do that. Move this one over, 1, 2 places, and this point could go over 1, 2 places. Should have the same shape, and I'm not going to be perfect with that. And then remember, this settles in but never crosses the x-axis. Okay, so that can be really useful for speed. Okay, so let's take a look now and see if we can implement those ideas. They're asking us to pick the graph, and you got A through H. Yeah, A through H. There's a whole bunch of them. But what I can see here is a normal parent graph. If I'm looking at this thing, a normal parent graph would be crossing right here, right? Something like that. And this guy is off by how much? It's down 1, 2, 3, 4. So this one has, so compared to the parent graph, this guy has, I'll do it in blue. The blue one has a vertical shift of down, what did I say, 4? 1, 2, 3, 4. Down 4, so a negative 4. So you have a minus 4, and that'll help us try to identify. We should have an exponential function and then a minus 4. And the only one I see that actually has that is D, right? Is D. So I would take D, and I might actually plug in some values because we're kind of new at this. I might take D, put a little star next to it, and maybe plug in some values just to kind of test it, right? So we can go ahead and plug in some values here real quick. Like what happens if I put in a 0? Now remember, I'm putting in 0 for x is what we're doing here. We're testing this one that we suspect is the right answer. So I wish I could always move that over, I guess. Move that over a little bit. Okay, so what is that function? It says 3 to the x minus 4, and what are we putting in for x? We're putting in 0. So 3 to the 0 is 1. 1 minus 4 is negative 3. Do we actually have 0, negative 3? And if I go 0, negative 1, 2, 3, yeah, we do have 0, negative. There it is right there. 0, negative 3, right? How about if we try just one more point? Let's try a positive 1. We put in a positive 1, remember, for x. So it's going to be, I'm looking at the function for letter D, and that just says 3 to the x, so 3 to the first, minus 4. Well, that's just 3 minus 4, which is negative 1. Is 1 comma negative 1 a point on my graph? And there it is right there. So I feel pretty good about this. Yeah, it's got to be D. And I really knew that before even plotting points because I knew that this thing had a vertical shift of down 4 by looking at the graph. And none of these have, look at A, I mean, it would have to have a minus 4 for me to start looking at it. And none of them have a minus 4, minus 4. There's the minus 4. There's only one. That one's plus 4, which would have put it up. Okay, so those are nice little clues to speed you along. This particular problem may seem a little bit confusing for some people, but what you still can do is you can still implement because there isn't, well, you still could implement something here. You can still take a look at what happens at negative 1 comma 1 over a. And the thing about this that gets a little bit tricky is that, you know, and this book doesn't talk about the reflections as much. But here, let's take a look at this. So what if we go like this? Instead of being at 0 comma 1, it's 0 comma negative 1 for the y-intercept. And then we've got negative 1 comma negative 1/3, and we got 1 comma negative 3. So it sort of looks like, you know, if we're trying to look at this pattern up here, right, this business about looking at the a value, it still kind of holds here, even though this particular problem said, hey, let's only look at a values greater than 1. But on this particular problem, since there really wasn't any shifting involved, there was actually a reflection. You can still see, look at that a value. I'm going to suspect that it's going to be this negative 3. So since you know, don't have a lot of experience with this, why don't we just go ahead and do some testing and see what happens. So let's go ahead and take f of x, and in this case we're going to use this idea of negative 3 to the x power. So once again, we're going to use a 0 first of all, and 3 to the 0 power is 1, but you still have that negative there. So this actually is going to be negative 1. And then let's take negative 3. And once again, the 3 is not in parentheses. The negative, rather, is not in parentheses. So that the negative is not being raised to a power. Let's try another number, like how about 1? And 3 to the first power is 3, and then negate it, so we get a negative 3. You know, and is this actually, in fact, matching the graph we have? And if we were to check it, we can go ahead and check it. Let's check it with a purple pen, and let's look at this point. This is 0 comma negative 1, 0 comma negative 1. Well, there it is right there, 0 comma negative 1, that point. And how about this point right here? This is 1 comma negative 3, and I've got a 1 comma, yep, there it is right there, 1 comma negative 3, which is this point. We could even check this point right here by putting in a negative 1 in for x. Right, we could put a negative 1 in for x and see what is negative 3 to the negative first. Let me make that a little bit clearer that it's an exponent. Okay, well, what is that? We still have the negative, and we've got 1 over 3, so it's negative 1/3. And that is that a point? Negative 1 comma negative 1/3. Yep, there it is right there. That is definitely a point, and it's right there. So that is the graph that we're able to do. And sometimes you have to kind of do some process of eliminating and actually plotting points when you're first learning this stuff to get it to stick a little better. Most of these problems are not being reflected about the x-axis. Look at this one. So where is that y-intercept? That y-intercept is actually right there, 0 comma 2. So that's telling us that this guy has been shifted not up by 2, be careful, because our normal y-intercept, this is such a tiny little scale, our normal y-intercept is going to be right there at 0 comma 1. So this shifted up by 1. So I'm going to say vertical shift up 1. Okay, vertical shift up 1. And you can also see something nice happening here. You can also see that it looks like this guy is, it's settling in with this horizontal asymptotes here. It's not crossing this horizontal line, and that is at 1. That is at y equals 1. Okay, so it has a shift up by 1. So let's see, what are our options? Do we have anything that's plus 1? And if I'm looking for candidates, well, there's plus 1 right there, minus 1. This is plus 1, but it needs to be plus 1 out here, not in the exponent, right? So that's not a candidate. Any other plus 1s? There aren't any. Well, that's got to be the answer then, right? Whoops. So that's got to be the answer. And we could also check with some test points, but I think we're good. So are we good? I think we're good. So you can go ahead and check with test point if you want. Okay, so let's go ahead and move on to number 9. So number 9, what did they ask us to do? I have to zoom out a little bit. It says graph the function f of x equals 2 to the x. Okay, we're starting to become familiar. That was a parent one I did at the beginning. State the domain and range of the function. Choose the correct graph. Well, what are 3 quick points I can pull from this? Right? There's the 2. The base is 2, so I know that negative 1 comma 1 over 2 is a point. I know that 0 comma 1 is a point, and I know that 1 comma 2 is a point, right? And so you can sort of glean that information real quick. What graph has those points? And man, they sure don't give us, they sure don't help us a lot with the sizing of this stuff. But what has a y-intercept at 0 comma 1? And are those counting by 2s? I hate this. Sometimes the scales 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No, they're not counting by 2, so that's good. So that looks like a good candidate. 0 comma 1 is a y-intercept. Well, what other points are we expecting to work? We're expecting 1 comma 2 to work. If I go to 1 and up 2, well, there's 1 comma 2. So that's working. And just to really check it out, how about negative 1 and then a half? And then negative 1, and I'll really zoom in, negative 1, let's see. Wow, this is negative 2 here, but that's down below. I really don't like their labeling. Negative 1, negative 2, negative 3, negative 4, negative 5. So this is negative 1 comma half, and that looks like, yeah, that's about half of 1. Negative 1 comma half. There's another point that we expected, negative 1 comma half. So we're really sure that this is it. The answer is B. Well, they would like us to answer the domain. Now we know the domain of all these exponential functions is going to be all reals. That's an easy question, and you could see it. This is going up to the right forever and to the left forever. That's going to be all reals for the domain. The range, however, never quite gets to 0. It's settling in, but never gets to 0. So it has to be open at 0, and it goes forever up, 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 up. So that's positive infinity. Okay. And let's flip the page or take a look or scroll or whatever we're doing here. We're digitally flipping the page. Number 10, graph the function, state the domain and range of the function. This is going to be h of x. Now look at that. Same old parent there of 2 to the x. But look where that x minus is. That x minus is up here in the exponent. So we know that's going to be a horizontal shift. Horizontal shift right 2 spaces. Okay. So we know what the basic 2 to the x looks like. This should look like the 2 to the x, but shifting to the right. And which one looks like a good candidate for that? I think C is looking pretty good. Let's zoom in on C. And let's see if that actually is happening. So the parent graph would have been right here at 0 comma 1, 1 comma 2, and then negative 1 comma half, right? But we just said, by looking at this, we're thinking that this shifts to the right too. Let's see if it did shift to the right 2. Take this point and go right 1, 2. Yep, looks good. Shift this one 1, 2. Yep, this one 1, 2. This is definitely shifted to the right 2. So this must be our graph. Okay, so what else do they want us to do? Probably take a look at the domain and range. And by the way, we could have gotten the domain and range before looking at the graph on this one, because we know that the domain is going to be all reals. And we also know that the actual range on this particular one is still settling in at 0 and going up and up forever to infinity, right? So this is going from 0 to infinity. How would the range change? The range would change if you had a vertical shift up or down. That would change the range, right? Because vertical changes the y, the range. Let's take a look at the next one. And this one might make you a little nervous seeing that e there, but remember, e is just a number. E is an irrational number, approximately 2.71, right? That's e. So this is, instead of having a base of 2, instead of having a base of 2 that we've seen, it has a base of 2.71, blah, 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 right? So it's going to grow a little bit faster than our base 2, because it's a little bit of a bigger base. A base 3 would grow faster than e. Okay, but other than that, it should have a lot of the same characteristics. Now, the only thing about this guy is what? Well, we have e to the x plus 3, so that must be a vertical, no, I just messed that up. That must be a horizontal shift. Remember, it's different, opposite than we think, so it is left 3. So what looks like it has a horizontal shift left 3. Okay, everything else should look very similar to our 2 to the x power. It's e, so it's a little bit, grows a little bit faster, but it should look similar. But then having a horizontal shift to the left. And notice these guys, since this dips down below it, it had a vertical shift down. This thing also goes below, so it must have vertically shifted down. This one's looking okay, but it's not growing, right? That base is, that E base, right, is something in between 2 and 3. So anyhow, a 2 to the x, I mean, it's going to grow, it's going to grow like this. It's growing. This thing is actually decreasing, so it can't be that. Must be this guy right here. Okay, and you could put in some values, but you don't really need to. After you see that those other ones can't possibly be the answer. And then now we want to write the domain. The domain is still going to be all reals. In fact, that's the answer for all these. And this guy is settling in, but never crossing the x-axis. So this is going to be approaching 0, never crossing it, and then approaching infinity, getting bigger and bigger, or taller and taller, or higher and higher, right? The y value is going up and up. Now let's see what happens here. Come on. This thing's got to shrink. And let's see what's next. Oh, okay, yeah, next skill. The next skill is going to be to solve a exponential equation. Okay, so exponential equations, once again, they're equations with variables in the exponent. So the very, very useful property to remember here is, let's just call this exponential property. Exponential property, a very useful one, it says if you have an exponent a to the u power and it equals the same base a to the v power, then we can actually just say that u must equal v. So we can simplify our problems down quite a bit. Now, I put this one in so you have a step-by-step to go back to if you wanted to look at it. Let me work this problem on the side just to show you how I would do it, and then we'll go back and fill it out. So this problem is we're going to start right here, which says 2 raised to the x plus 2 power equals 32. Now you can guess and check it, but we're trying to get away from that kind of thing. So if you look at our property once again says if you have the same exact base, then you can set the exponents equal to each other. So wouldn't that be awesome if we knew that we can write 32 as a base of 2, because then you would have the same base. And it's not just awesome, it is going to happen, right? Because 2 to the 4th power is 16, 2 to the 5th power is actually 32. Let me just write that over here. 32 equals 2 to the 5th power. And so we just rewrote it as 2 to the 5th power. Now that we have the same exact base, it's really easy. We just take the exponent and say x plus 2 must equal 5. Now solve that one. That's really easy to solve, right? Subtract 2 on both sides and we get x equals 3. And we're done. So let's go with our step-by-step here. Once again, it's saying, hey, wouldn't it be nice if I can rewrite this as 2 to some power, and you can, 2 to the 5th power. Okay. Well, being that they both have the same exact base, I can now just write the exponents as equal. So that's just x plus 2 must equal 5. Good, and it's just using that property right there that we have identified above that I wrote down already. Now we want to solve this, and we can solve this by subtracting 2 on both sides. Here we are right here, subtracting 2 on both sides of the equation, and 5 minus 2 gives us 3. And that's the same thing I got over here. They go ahead and check it by verifying it, and they find out that it's true. Let's go ahead and do this problem, these types of problems now. So what was sort of the moral of the story here? Well, if I can rewrite this as a base of 5, and you have a calculator, you can figure it out. You can say 5 to the whatever power and kind of guess and check it. It shouldn't take too long. And when we do this, 5 raised to the 4th power, in fact, is 625. So I'm going to rewrite 625 as 5 raised to the 4th power. Now I got 5 raised to the negative x on the left. And since the bases are the same, once again, the bases are identical. Therefore, we can rewrite this as negative x equals 4. So x equals negative 4 by multiplying both sides by negative 1. All right, let's keep this going. 32, maybe a little side note over here. 32 equals, now the target base that we're going for is a base of 2, right? So that's what we're going for. And we've got 2 raised to the x minus 2 equals, and 32, in fact, can be written as 2 to the 5th power. So 2 to the 5th power, bases are the same, so now I can just rewrite this as x minus 2 equals 5, add 2 to both sides, and we get x equals 7. Okay, this is number 14, x equals 7. Once again, if you suspect anything, you have time on the test or whatever, you could always double check this by plugging this back in by running a check. Let's go ahead and run a check real quick. We're going to check this. The original problem was 2 raised to the x minus 2 is supposed to equal 32. So we go ahead and put our answer in. We got a purple 7 rather, not negative. And now we go ahead and write up there, what is 7 minus 2? Well, that's going to be 2 to the 5th. And we know 2 to the 5th is actually 32. So it checks out. Good. Now, this one might stump you a little bit because you see a base of 4. You see a base of 4 right here, and you go, well, I want to write 8 as a base of 4. And you cannot write 8 as a base of 4. But what you can do is you can write 4, I'll just write 4, as 2 to the 2nd, right? Isn't 2 to the 2nd still 4? All raised to the x. And 8 can be written as 2 to the 3rd. So now you have to remember rules of exponents. A power raised to the power is multiplication. So this on the left is 2 raised to the 2x. Now our bases are the same, so 2x must equal 3. All we have to do is divide by 2, and we got our answer. X equals 3/2. Number 16, getting a little tougher. Our first hope or option is that we can rewrite 243 as a base of 3. So we take a look at that, and we kind of mess around with our calculator a little bit. 243, can we write it as a base of 3? And by using your calculator, you can write 3 to the 4th, 3 to the 5th, and 3 to the 5th actually does it. So we are going to rewrite. Now let me use some color just to highlight something. I'm going to rewrite this as 3 to the 5th. Now you cannot forget that it is raised to the x power. So now we have 3 raised to the x squared plus 6 equals, now we know a power raised to power means you're going to multiply. So it's going to be 3 raised to the 5x. And on the left, we have 3 raised to the x squared plus 6. So the bases are 3. The bases are the same. So we can now rewrite this as just an equality of the exponents. That's x squared plus 6 equals 5x. Well, that's still a simpler equation, but it's quadratic, right? So we want to set it equal to 0. By subtracting 5x on both sides, plus 6 equals 0. And of course, we're now going to factor what multiplies to 6 and adds to negative 5. And that's just negative 2 times negative 3. So this factors down to x minus 2 times x minus 3 equals 0. Set each factor equal to 0, and x equals 2. Or set the second factor equals 0, x equals 3. And we have two answers on this one. X equals 2 or x equals 3. Number 17. Yikes, look at that nasty thing there. Well, I'm seeing a base of 12. So I want to see, can I rewrite this as a base of 12? And I can. 12 squared is 144. And don't forget, you still had that raised to the x power. This is 12 raised to the x squared power. And now that beast right there needs to be dealt with. We have to figure out 20,736 squared. Okay, well, anyhow, I'm just going to deal with this number first. And our goal is to get it as a power, a base of 12 rather. So, I kind of messed with the calculator a little bit. 12 to the third. I think I put 12 to the fifth. That was too big. 12 to the fourth was just right. Sounds like a Goldilocks story time. Anyways, 12 to the fourth is 20,736. So I can replace this right here with 12 to the fourth power. Do not forget that there was that black second power hanging out of there. You cannot just lose it and forget it. Now we do know a power to a power is multiplied, right? So we've got 12 to the 4 times 2 is 8. And also, when you are multiplying these two factors, multiplying them, what do you do the exponent when you're multiplying with the same base? You add the exponent. So that's just going to be 12 raised to the x squared plus x. We just added the exponents. Well, look at that. The bases are the same, so that's a beautiful thing because now we can rewrite this as x squared plus x equals 8. Of course, it's quadratic, so we set it equal to 0 by subtracting 8 on both sides. And we ask the good old question, what multiplies to negative 8 and adds to 1? Did I lose something? I lost something somewhere. Ooh, there it is right there. Darn it. I got to go back. I got to do a redo. The power of editing would make me look better, but I just don't want to do any editing. I'm just going to keep on rolling here. So notice this is 2 raised to the x. So power raised to power is multiplication, so that is 2x. And this is 12 raised to the x squared. And this is 12 raised to the 4 times 2 is 8. We try again. Now, remember, when you're multiplying two numbers with the same base, what do you do the exponent? You add them. So I'm just going to put it in this order. It's just going to be 12 raised to the x. It's going to be x squared plus 2x. That equals 12 to the 8th. Now, here we are again. The fact that the bases are the same, we can now set the exponents equal to each other. And it's a quadratic, so we set it equal by subtracting 8 on both sides. And then we ask the good old question again, this time with the right problem. What multiplies to negative 8 and adds to 2? Well, isn't that going to be a positive 4 and a negative 2? And that is correct. X plus 4 times x minus 2 equals 0. Set each factor equal to 0, so x equals negative 4. Set that factor equals 0, so x equals positive 2. And there we go. We've got the two answers, a negative 4 and a positive 2. Number 18. All right, so we're looking at this, and what kind of common base can we use? And that, if you said 2, you're correct. Base 2 is what we're going for here. So we already have that base 2, so how about 8? 8 is considered 2 to the third. And 4, well, 4 could be written as 2 to the second. So and let me use another color. So 2 to the second is replacing the 4. Now don't forget that that 4 was raised to the x minus 7 power. That cannot be forgotten. And another thing is that, you remember, a power raised to power, you would have to distribute that when you do that step. Let's do that step right now. So 2 raised to the, now distribute your 2 raised to the 2x minus 14. And on the left, when you're multiplying two numbers with the same base, what do you do with the exponent? You just add them, so that's x plus 3. Okay, the bases are the same, so now we can set the exponents equal to each other. So we've got x plus 3 equals 2x minus 14. So I think I'm just going to go through and subtract x, which gives me 3 equals x minus 14. Add 14 to both sides, and I get 17. X equals 17. And if it bugs you write it that way, you can write it x equals 17. Now, I believe that the my math lab likes to write it using this braces, which is more like set builder notation, but it's just individual numbers. Anyways, whatever. If they want that, you got to do it that way, right? But of course, this way is how we often do it as well. Now, solve. You see the E, you get a cold sweat, because E, yeah, what is that? Well, E is just a number, okay? It is irrational, but it's just a number. So, and look at the bases are the same. And if the bases are the same with this equation, then you could just set the exponents equal to each other, and this problem is not looking so bad after all. In fact, it's not even quadratic, right? It's just first power. So that means I want to get all the x's together, right? Something like that. You can go the other way if you want to. But anyways, 1x and minus 8x is negative 7x equals 21. Divide by negative 7. And x equals negative 3. And there you go. X equals negative 3. I think we have one more on this page. Another one with E, but once again, E is just an irrational number, but it is a number, not a variable. Now we've got a power raised to a power, so right, this is E raised to the 7x equals E raised to the 8x minus 4. Well, they both have the same base. If they both have the same base, then we can set the exponents equal to each other without any problem. And you can move these any way you really want, but we do need to isolate the x. So we end up getting a negative x equals negative 4. Multiply both sides by negative, and we know x equals positive 4. And we're done. All right, let's take a look at the next one, and I need to zoom out because it looks like we got some reading to do. We actually have a formula to take a look at as well, and this is called compounding interest. Oh, wow, my knee, I'm getting old. Anyways, compounding interest, ouch, it hurts. Compounding interest formula, and so the formula looks something like this. A equals P times the quantity 1 plus R over N raised to the N times T. So I think what I want to do is zoom in over here and fill in some of these pieces using color. So P is called principal, and it's the starting amount of money. Like if you're putting money into an investment, a CD or something, P is the starting amount of money, the principal. Let's call it starting amount also. Starting amount. Okay, what is A? Well, A, whoops, I'm not supposed to have that color. A is just going to be the accumulation of money, or the accumulation, or the amount in the account. It's what the money's growing to. So A is the amount that's growing, the future value of the money in the account. What is R? R is your interest rate, written as a decimal. N, that's a weird one, huh? N. And that shows up in two locations right there. And N is your compounding periods. A lot of times students go, what the heck are you talking about? Well, if they say it's compounding, let's say monthly, how many times does that happen in a year? 12, so N would be 12. If they say compounding quarterly, how many times does quarterly happen in a year? That would be N equals 4. So that's what those numbers are. And the last one is T. I've got another color, T. And T is just going to be your time. Usually in years, but it could be in months, depending on how the problem's set up. But with these problems, it's usually years is what we're talking about. Okay, let's see if we can do this problem now. So suppose that you deposit $4,993 into a certificate of deposit, also known as CD, today. Determine the future value A, there it is, A, future value A of the deposit if it earns 9% interest. So we've got some important little pieces coming here. We've got the starting amount right there. Maybe I'll try to use the colors of I used blue. So there's your principal. And we've got our interest rate, which I did in red. But, R is going to equal 0.09. It must be written as a decimal. And now it says compounded monthly, which I used purple. Compounded, oh, wow. Come on. Compounded monthly. So that would mean N equals 12. What else? Oh, and then in the actual problem A, it'll tell you how for how long. And I used green for time. So T equals 2 there. All right, well, let's go ahead and do A. So here's what we do. The amount of money is going to be the principal. The amount that accumulates in the account is going to be the principal, $4,993, times 1 plus the interest rate, which we said was 0.09, divided by compounding periods. It's monthly, so it's 12. And that's raised to the, and I need to get that out of my way, it's raised to the compounding period of 12 times the time. In this particular one, A says that they're going to do this for 2 years. I guess we'll do 1 in the right color. All right, so now we simplify this down just a bit. And remember order of operations in the parentheses. Got to do that first. So you're going to type in 0.09 divided by 12 plus 1. And when you do that, you get 1.0075. Of course, 12 times 2 is 24. So now you need to do the next bit of fun that is order of operations. you take that base raised to the 24th power and then multiply it. And then when you do all that, well, we're going to get an approximate value, and you get approximately $5,973.69, and these are dollars. So that's what is accumulated in the future value of 2 years with the situation of having an interest rate at 9% compounding monthly, starting with $4,993. All right, there's the first one. Let's do the next one, which is B. Well, B, all they're doing here is they're having the same exact situation each time, but they're trying to see what happens to the money on B when you compound it. In this case, you're compounding it for 3 years, so T equals 3. So that's the only thing that's changing with these three problems. So let's start with A, and we're starting with the same amount, $4,993. And the reason why they're doing this is they're trying to see if you can identify or see if there's a difference when keeping the money compounding longer. And I think you probably know if you let the bank have your money for longer, they're going to give you more money for that. So compounding 3 years should make more money. So here we are, same situation. It's compounding monthly still, but in this case on part B, we're doing it for 3 years. Right there, 3 years, okay? So now we do the same thing. We multiply, or we divide rather, 0.09 divided by 12, and then add 1. We get 1.0075. That gets raised to the 12 times 3 power, which is 36th power. That must, after we do all that, we multiply it by 4,993. And when we do that, whoops, let me see something here. Okay, so then when we do that, we raise it to the 36th power, and then we multiply it by 4,993, and we get approximately how much money? $6,534.07. So yep, it did grow more. Well, it had a whole year more growing, so it grew quite a bit more, right? So you're making 9%. These numbers, 9% in a CD, oh my gosh, when did they actually write this problem? Because 9% was many years ago. I mean, if you look at a CD now, it's not even 1%, which is just very sad when you're trying to save money. Anyhow, C, so it's encouraging. It will encourage you, right? When CD rates are that low, it encourages you to go in the stock market or do something else, right? Because the pathetic little bit. The nice thing about CDs is they're guaranteed. So now you have to go into more risky areas. All right, letter C. What happens with the letter C? The question for letter C, it says everything's the same except for 5 years. So in letter C, where our T becomes 5. Okay, so that's the only difference. So we've got the amount of money is the same starting amount, $4,993 times 1 plus interest rate of 9% divided by 12 monthly compounding periods, raised to the 12 times, and then this C is for 5 years. So just like before, we divide first, then we add 1, we get 1.0075, and that gets raised to the, what's 12 times 5? 12 times 5 is 60, so 60 to the power, and then multiply it, and we should get approximately $7,817 and approximately 45 cents. There we go. All right, there was our first. Whoa, that's not what I wanted to go to. Get out of there. Oh my gosh. Okay. This thing's freaking out on me. Okay, so here we are. Let's go to the next problem. Next problem is another exponential problem. Another exponential type of problem would be, now we're compounding, we're doing the same formula, but what's changing this time? The compounding period. So what color did I use for compounding periods? I used the purple for N. So here's what's changing. For A, they're compounding it annually. And annually, how many times does that happen in a year? So N is 1. How about compounding quarterly? N is 4. Monthly, n is 12. And daily, how many days happen, how many days happen in a year? Daily is n equals 365. Okay, so you can see what's going to happen here. Let's go ahead and see if we can do this problem. I think with this one I'm going to try to space it out a little bit differently. So at least on this first one, well, we got to read the problem. Suppose that you deposit $3,000 into an account. So 3,000 would be the principal. That's P. An account that pays 9% annual interest. There's your R written as a decimal point. If I ever want to print this out, I probably shouldn't be writing right across 2 pages. So this is R equals 0.09. And how much will you have left? Wait, what are we doing? Suppose that you deposit. How much will you have after 4 years? So that's our T value. So that's T equals 4. I don't know why I'm all of a sudden concerned about when I print, if I ever print this for anybody. Okay, so T equals 4. So now let's go into our mode here of trying to solve this. A equals, well, the principal once again is $3,000. It's 1 plus, what's the interest rate? Same thing as last, 0.09. And then on the very first one for A, remember A we said compounding annually. So 1 raised to the 1 times, and then what's our time? Every single time, our time is going to be 4 on each one of these they're having us do. So that stays the same. So I'm just going to make that black now because that's not changing. The only thing that changes, the purple, is the compounding periods. Anyhow, when we do this interior part, we get 1.09, and that gets raised to the 4th power, and then gets multiplied by 3,000. So now we get our approximation, and when we multiply this, so once again, 1.09 raised to the 4th times 3,000, we get about how much money? $34.74. Now, by the way, if I'm in class, I usually do a problem talking about if you started with like maybe $10,000 and how much would you have if you're 25 and retire at 65, like in 40 years, and it ends up being a lot of money. So compounding interest is really kind of interesting. First time you really see it in power, in full power, like in a over a long period of time, because it's growing exponentially. So remember, exponentially grows faster and faster over time. So if you're able to leave that money into a nice growing account, at the end it's making a ton of money. I don't know I think it was considered one of the wonders of the world. I think it is. At least it is a wonder for me, because I just love compounding interest. Anyway, so let's go to B. Let's do B right here. And so it's A equals $3,000, 1 plus our interest rate. And on B, what do they want our compounding periods? Quarterly. Maybe I'll write that up just so you can kind of get used to that language. Then when they say quarterly, they mean n equals 4. So 4 goes there, 4 goes there. And how many years? 4 years. Okay, so now we've got, 3,000. We, of course, divide 0.09 divided by 4 plus 1. And when we do that, we get 1.0225 raised to the 4 times 4 is 16th power. Of course, you do the math, and we get A equals approximately how much money? $4,282.86. They're trying to give us an idea, what happens. Now, everything else is the same, but this one is, the first one was compounding annually. Second was compounding quarterly. And let's take a look. Ooh, whoops, what happened there? Next one's quarterly, and that's AB. Let's do C. Ooh, I really... space is not working out here. Okay, so now C. Now let's see, what was the difference on C? Part C right here says compounding monthly. So let me just write that up for us. For C, it says compound language, compound monthly. That means n equals 12. All right, so what's the formula again? It's A equals principal $3,000. 1 plus 9% divided by my compounding periods. Compounding periods is monthly, so it must be 12. Simplifying this a little bit, we end up getting 1 point, well, it's like the last one, 007, or the first problem we did, 75. And then 12 times 4 is 48. So we raise it to that power, multiply it to 3,000, and the accumulation in the bank, we have about, how much money? $4,294.22. Okay, D. D said it needs to be compounded daily. Yikes. Daily. How many days in a year? 365. It's going to be a big number, at least the exponent. Well, same formula, starting with $3,000, 1 plus interest rate, still for 4 years, but the compounding, by the way, 365. So you're compounding daily, and I remember the first time I heard about that, that sounded too good to be true. Like, wait, it gets compounded every day at 9%. Well, wait, well, let's look what's happening. The 9% is getting divided by 365 also, right? If it was getting compounded, this is really messy over here. It kind of bugs me. I'm gonna redo that. If this thing was getting compounded 365 times a year, which it is, but at a rate of 9%, it would be way bigger than anything else, right? But we take that 9% and divide it by 365 into 365 little pieces, right? It still ends up being more than if you don't do that. So if you compound more, you're going to get more money. But it's not, our first one was compounded once every year. The first one was that, compounded once every year at 9%. But then we went to monthly. It happens 12 times a year, but it's not 9% 12 times a year. It's 9% divided by 12. Okay, so it ends up being more, but it's not 9% 12 times. Okay, anyhow, we do the math on this last one. And since these numbers are getting a little bit, I guess, tougher to, I just want to give you a little more detail so you can see when you, this was times 4. So then when you divide 0.09 divided by 365, add 1, and then raise it to this power, you should get a number that looks something like 1.000246575 ... It keeps on going, right? And then okay, my numbers are looking, I got to do it right now on the calculator because something's looking a little bit weird. This is a 1. So we've got 0.09 divided by 365. Then I add 1 to that. And that's my 1.00 blah, blah, blah. Okay, so then I've got 365 times 4, which is, so this is raised to the 1,460th power. So let me do that real quick. So I take, oh my gosh. So 0.09 divided by 365 plus 1. Raise that to the 1,460th power. and I'm getting approximately 1.43326,581, and that must be multiplied by 3,000. 433, yeah. And so that's going to give us, now this is approximately, these are all approximately now, we had a round. Now when we multiply that, we get how much money? We get $4,299.78. Almost breaking 4,300. So there it is right there. And then they ask us this little question. Well, I thought they asked the question on this one. Oh, they asked it up here. So let me zoom out. They asked us a little question at the very beginning. More compound, here it is right here. Whoops. More compounding periods per year, blank the future value. Blank the, anyways, that sounded funny for some dumb reason, probably because it's 220. Anyhow, it increases the future value of it. Increases, right? The more you compound more often, the more you make. But like I said, that rate gets divided also by that compounding period. So look at compounded annually was $4,234.74. Compounding it daily was $4,299. Okay, a little more. Those differences, they don't seem like much, and they're not like huge differences over 4 years, but over like 40 years or many years, it becomes a huge difference. Okay. All right, and our last problem is half-life, and I picked 3 of these word problems, and I start getting tired at the end here. But anyways, and I start regretting, right? But I really did want you to see the money side of things, and also half-lives are real common. So the way that a half-life works is, so let's read this problem. It says the half-life of carbon-10 is 19.26 seconds. Wow, that's pretty fast. Suppose that a researcher possesses 200 grams of 200 grams, a 200 gram sample of carbon-10. The amount A in grams of carbon-10 after T seconds is given by the following equation. So the half-life, if I started with 100 grams of this carbon-10, being that it has a half-life of 19.26 seconds, that means after 19.26 seconds, if I start with 100 grams, I'd have half of it, 50 grams. And then another 19.26 seconds, I'd half of the 50, I'd have 25 grams. So that's how a half-life works. And if you keep on having something, half, it seems like you're going to get to 0, but you never would get to 0 technically. So when you're running these half-lives, you never actually get to 0. And that's kind of, if you have super accurate ways of measuring things, you could actually measure time on something that's really old. So they do carbon-14 testing, and its decay is super slow. So they're able to, by looking at its half-life, you can get an object from antiquity or from way back in history, do a carbon-14 date testing on it, and by using this formula, it's by using half-lives, you can test how old something is, right? Now they ran into some problems because you're testing carbon, and maybe in the medieval days there was some group that was stealing something else and causing fire to happen, and fire will scorch it and mess up your carbon readings, and you could get wacky data. So I think they've gotten better at that, but I'll stop talking about that now. So the half-life, let's see, part A. Oh, another thing I'd like to say before I start, and I really do want to finish, but if time t equals, we said time t at 19.26 seconds, that's a half-life. Look at this thing right here, right? The exponent. The exponent says we got 19.26 on the bottom. So when t equals 19.26, what is 19.26 divided by 19.26? It's 1. And then that means we would have a half raised to the first power, which is just a half, and then half gets multiplied by the starting amount, 200, and it gets halved. So that's kind of how that formula works. Just get rid of that stuff. Even though this is not a business problem, right? You still have, so you wouldn't call this principal, but it's still doing the same thing. It's still your starting amount. In business, we call that the principal, right? Now, this would be a sucky formula because every 19.26 seconds, your investment would be cut in half. Yikes! That would be a stock market going out of control down. We wasn't sure with the election, all this stuff happening, what was going to happen. But anyhow, so part A, let's do it. Part A. What are they asking on part A? How much carbon 10 is left in the sample after 1 second? Well, that means, so let's use some color here. There's the one variable we have. So on number 1, that would be t equals 1. So if I was going to use that formula down here, which they gave it to us, let's use it. Starting amount of 200 grams of this substance raised to the times a base of half raised to the t. So for after 1 second, and this is all over 19.26. So when you're putting this in your calculator, probably a lot of people are going to, instead of write the fraction, they're probably going to write 0.5 because 0.5 is exactly a half. And then they're going to have to, I used parentheses here to make sure that this stays in the exponential. You have to use a caret button or an exponential key to put it up there. And then, so you raise it. Let me go ahead and show you what that looks like number-wise. You should be getting something approximately at 0.964, it's too much detail, 526. Anyhow, you multiply that by 200 and we get how much of this carbon 10 is left after 1 second. Starting with 200, we still have 192 point, what did they say, round to the nearest thousandths? Okay, so 192.930, and these are grams. That's what's left after a second. This stuff decays pretty dang fast. So just trying to kind of consolidate here so I can squeeze in part B on the right side of the screen. So once again, we got the amount starting with 200 grams of this carbon 10. There's my half-life. And in this case, on part B, what is T equal to? On part B, it says T equals 19.26 seconds. Well, that's convenient. That's a full amount of time that triggers our half-life, right? Because all of this now just equals 1. And so now we've got, take half of 200, and so what's left is 10. So after 19.26 seconds, we have, did I say 10? 100 grams of carbon 10. Now let's go ahead and work our way down here to part C. If I can get this to work, part C. So part C, once again, the formula amount equals 200 grams starting amount, half-life, and what was the time frame on part C? So they're saying T equals 38.52 seconds. I think that's exactly double the half-life time, so you know what's going to happen there. But that's going to be 38.52 over 19.26. Now, this stuff right here just simplifies to what? Just a 2. Okay, so anyways, now we have 200 times half, or 0.5 raised to the second power. And half times half is a quarter. And a quarter of 200 leaves us with 50. So the amount is 50 grams. You have 50 grams left of that carbon 10, starting with 200, after 38.52 seconds. And then finally, part D. Starting with 200, half, 19.26. Let's see. On part D, how much is left after 100 seconds? So that would be T equals 100. We put a 100 in here. Hey, okay, so we basically have a half raised to 100 divided by 19.26. And I'm just going to give you some detail. That is approximately 0.0273539 and so on. Approximately. So how much is approximately left after 100 seconds? Well, we're all the way down to 5.4. Wait, how many decimal places? Thousands. So 5.471 grams after 100 seconds. And that is it. And we are done. And I am totally done. So I'm fried. I'm done. So I hope you're having a great day and take care. I'll talk to you soon. Bye.